In the last lecture, we studied R-enriched trees. In this lecture, I am going to introduce the notion of an R-enriched endofunction. This will be very helpful in proving in the next lecture the Lagrange inversion formula. So what is an R-enriched endofunction? As before, let R be a species of structures. Then an R-enriched endofunction structure on U consists of, firstly, an endofunction structure on U. So a function S from U to U, and secondly, for every U in U, an R structure on S inverse of U, on the fiber of U. So this picture is a schematic diagram of an R-enriched endofunction, and these green arcs indicate R structures that are being put on the fibers of points. So I'm thinking of the function S as a directed graph, taking each point to its with a directed edge from each point to its image, and this is the picture you would get there for an R-enriched endofunction structure. And so we define end RU, end R to be the species for which end RU is equal to the set of all R-enriched endofunctions on U. And transport of structure is defined in the obvious way. I will not go into it. There's also a notion of an R-enriched partial endofunction. So if I want to make, I can just modify this definition a little bit. An R-enriched partial endofunction on U is a function, then I will not say from U to U, but rather I will say S from V to U, where V is some subset of U, and the rest remains the same. So an R-enriched endofunction is of course a special case of an R-enriched partial endofunction, where we take the domain to be a domain V to be all of U. And here in this picture you see an example of an R-enriched partial endofunction. There are 3 points here which do not have any images. They are these 3 points 22, 23 and 24. So this is an R-enriched partial endofunction structure on the set of 24 integers, and 3 points here do not have any images. So the domain V is equal to 21, but the domain could be any subset of 24. It doesn't have to be the first few elements. And the main theorem about this species is that the species of R-enriched partial endofunctions satisfies the identity that it is an assembly of R-enriched trees times an R-enriched endofunction. So you can describe partial endofunctions in terms of R-enriched trees and R-enriched endofunctions. This is not difficult to prove, as is clear from this picture. You see, when you have a partial endofunction, you'll have some points which do not have any image, and those will be the roots of rooted trees. These arrows are now just pointing towards the root, and Otherwise, you will have just an endo function. So you separate out the connected components which contain the points which are not in the domain of the partial R-enriched partial endo function, and that will be an assembly of trees, and what remains will be a complete R-enriched endo function. So this picture shows that end RP is equal to EAR dot end PR. I'm giving these proofs in terms of pictures, but it's perfectly possible to sit down and write down the bijections between these sets explicitly. Let's look at some examples. So firstly, if you just take E-enriched endofunctions, this species is just the same as end, because E means you're just taking the set, you're not putting any additional structure on it. And of course, end PE is equal to end P, partial endofunctions. An interesting example is that 1 plus X enriched endofunctions is just permutations. And why is that? Well, the point is that you have this underlying endofunction S from U to U. Then the fiber of each point where S inverse U has a 1 plus X structure. What this means is that S inverse U is either singleton or empty, which is the same as saying that S is injective. But S is an injective function from a finite set to itself, so therefore it must be bijective, and hence a permutation. What about partial endofunctions? Well, so you will have some components in the endofunction directed graph which do not have, which are trees, and those trees will have to just be lines, because each node is only allowed to have a single or no child. So what you get is that P1 plus X is EL plus times S. Okay, now let's take a few more steps towards understanding R-enriched endofunctions, and I'll show now that the species of R-enriched endofunctions is the species of permutations on X dot R prime. Remember the derivative of AK AR and this is equipotent. I'm using this symbol here to denote equipotence, which means that the number of structures on a given set are the same for both these species, but the species may or may not be isomorphic. Now, since S is isomorphic, equipotent with L, I can replace this S with an L here. So end R is equipotent with with L of X times X dot R prime. Let me try to explain the proof of this. So this is again proof by pictures, and here on the left you see an R-enriched endofunction on a finite set, described in the usual way by a directed graph, and these green arcs depict R structures that are being put on fibers. So what you do now is that each of the components of this graph consists of a cycle which could be of just length 1 and a bunch of trees that have their roots on the cycle. So what you do is you take each of these. So for example, let's look at this node here which is on this 3 cycle. What you do is you separate it out from the cycle, and you just take this tree that is attached to it. So in this case, and then you remove this node. So what you actually get is an R prime assembly of trees. Each of these branches here can be thought of as a tree in their own right. Let's look at this example here where we have this piece. So here I have pulled it out, I have removed the root, and what I get are these two branches give me 2 R-enriched trees. But then there's also an R structure on this. There's this edge which is coming in from the cycle, a part of the cycle, and the R structure on this node which was on the cycle also includes that. And so what this piece of the picture is depicting is really an R prime structure, because I have this additional node, an R prime assembly of AR structures. So what we get is each of these nodes on the cycle give rise to an R prime assembly of AR cycles. But these nodes are on cycles, so what we really have is a union of cycles of R prime assemblies of okay, and this X denotes this point here which we had removed, because this is a point in U, so we can sort of separate it out. Maybe I can put it in a different piece in each of these things. So here, each of these we have the point X, which I should draw separately. So each of these pieces is an X dot R prime AR structure, and they are lying in cycles. So overall we get an S assembly of X dot R prime AR structures, and that's the proof of this result. Okay, and I'll give you one more interesting result which helps us count partial R-enriched partial endofunctions, and this will be related to one of the earliest lectures where we studied powers of species. So theorem: let U be a set of cardinality n, V be a subset of U, and let's say V has cardinality k. Then the number of R-enriched endofunctions S from V to U with domain V, so to speak, I should say partial endofunctions, the number of R-enriched partial endofunctions with domain V is given by Rk of n. Remember, this was defined to be the cardinality of, you take the nth power of the species R and take the number of structures on a set of size k. So to prove this, without loss of generality, you can assume that V is U is the set of all U is the set of integers 1 to n, and V is the set of first k integers. An R-enriched partial endo function on n with domain k consists of an endo function S from with domain k, so it's a function from a partial endo function, a function S from k to n, together with an R structure on Zi on the pre-image of each point in n. So what we get is Zi, Z1, Z2, Zn. These are R structures, and the union of the domains of these R structures are on sets. Zi is an R structure on Ui, some set Ui, which is the pre-image of S inverse I. And what we have is that U1 union U2 union UN. Well, this has to be the domain of the partial endo function f, so this is going to be k. So this Z1, Z2, Zn is nothing but an R to the n structure on k. And so what we get is that the number of R-enriched partial endo functions with domain k is just the number of R to the n structures on the set 1 to k.